This is the second instructional video on circular and rotational motion. This one is focusing on the force of gravity. Now we're not talking about force of gravity as mg. We're talking about the force of gravity between any two objects with mass. And what the law of gravity tells us is that any two objects at any place in the universe, if they have mass, they are gravitationally attracted to one another. Now, that's a lot of stuff in the universe that's constantly pulling on, tugging on everything. So why does it really not affect much of what we see and do with our everyday lives? It's because gravity is the weakest of the four natural forces, but it does have the longest range, stretching distances of billions of light years. So all the mass at the center of the galaxy is actually impacting our solar system, forcing it to orbit the center of our galaxy in a very, very long, drawn-out path. So what this means is you are gravitationally attracted to everything you see. Students in the classroom, a coffee mug, a water bottle, a tape roll, a brick, a building, a blade of grass, the sun, the moon, the earth, Jupiter, everything. You're gravitationally attracted to everything. So why don't we actually feel it? And it's because the force is extremely weak. Human sensitivity takes about 0.1 newtons of force in order to sense, which is on the order of about a 10 to 15 gram mass being held in your hand. You don't even really recognize the weight until it gets above that. A human being gravitationally attracted to another human is on the order of about 10 to the negative 8th newtons, even at close ranges. Now, the Earth is the only thing large enough near us that we can actually feel. But the sun and the moon do pull on us and on the Earth, and they do shape the way our lives exist. The sun is actually responsible for keeping the Earth in orbit around it. If it wasn't for the sun's gravitational pull, the Earth would just drift off into space. So the sun keeps not only the Earth, but all of the planets in orbit. Without the sun's gravity, the planets would just drift off into deep space. The moon is responsible for the length of the day. By pulling on the Earth, it actually slowed it down. The Earth used to rotate so fast that a day was 6 hours long. Over the course of about 4.4 billion years, the moon has slowed the rotation down to 24 hours, which we observe today. In billions and billions of years from now, long after the sun is gone, assuming the Earth and moon are not destroyed in the process of the sun dying out, the Earth and moon will actually become tidally locked, and it will be about a 27-day rotational period for the Earth. On a more important feature for us, seeing as we have a 24-hour day and it's going to stay that way for a while, the moon on our time scale impacts oceans and large lakes, and it does this every single day. The moon tugs on the bodies of water, and it creates a large bulge in them. These result in water being pulled into the ocean, creating a low tide, or being pulled onto the land, creating a high tide. So every day, every coast experiences 2 low tides and 2 high tides. Depending on other geological features determines how dramatic the tides are. Some of them are so minuscule you don't even really notice unless you're really paying attention and looking for it. Others can result in the ocean coming inland 1 to 2 more miles farther in than it normally does. So back to the actual force of gravity and just the basics behind it. The force of gravity is G, a gravitational constant. That is 6.67 times 10 to the negative 11th newtons times meters per kilogram squared. Now, the value of G literally means if you have a 1 kilogram mass and a second 1 kilogram mass, and you place them 1 meter apart, the force they will experience is 6.67 times 10 to the negative 11th newtons. In the equation, m1 and m2 are the masses of object 1 and object 2. R is the distance between the two objects. We're choosing to use R instead of D because a lot of our force of gravity interactions are going to be with planets and moons and stars and whatnot. So we're going to be referring more to the radius of the orbit itself, and that's why we chose R instead of D. Now, this, if we take, for example, the Earth, what is the force of gravity human experiences? We have, in the past, just simply used the force of gravity equals mg. Now, if we were to use this new longer equation, we would have g times mass of Earth times mass of person divided by the radius of the Earth squared, since the distance between the center of the Earth and a human on the surface of the Earth is the radius of the Earth. So what that results in is an equation for acceleration. It doesn't matter if you're on a planet or moon or asteroid or whatever. The acceleration you experience is g times m divided by the radius squared. That comes right from here. When we take a look, g mass of Earth divided by radius of Earth squared, that value right there is g, or 9.81 meters per second squared. That's why it works only for the surface of the Earth, because if you were to go higher above the Earth, then your radius from the center of the Earth has increased. So once again, the acceleration on any body, a planet, a moon, an asteroid, a star, if that was possible, is g, the gravitational constant, times m divided by the radius squared. Thank you for watching.